is able to see my screen now. First of all, let me thank all the organizers. Thank you very much for hosting me here. I'm very happy to present this joint work with Fabrizio Cipollini and Fabrizia Mealli. As you all know, the Rubin Causal Model allows to define the causal effect of a treatment as a contrast of potential outcomes and to develop methods to estimate causal effects under a previously discussed set of assumptions. In time series settings, the identification and estimation of causal effects have been already formalized in the context of randomized experiments. And in observational studies, there are many methods exploiting longitudinal information as well, the most popular being difference estimators, synthetic controls, and also their combinations. However, these methods usually require some control observations that we do not have in the context of our empirical application and often rely on functional form assumptions, such as the parallel trend assumption for the difference estimator. A little far away, maybe in the econometrics literature, intervention analysis employs ARIMA models to assess the impact of shocks on time series. So it doesn't need either control observations, but fails to define the causal estimates and to discuss assumptions enabling the attribution of the uncovered effect to the intervention. So we wanted to close the gap between causal inference under Rubin and intervention analysis. So that's why we proposed this approach, C-ARIMA, to estimate the effect of an intervention in observational time series settings under the Rubin Causal Model. So the C-ARIMA approach has two pillars. From the one hand, a causal framework under the Rubin Causal Model comprising all the set of assumptions allowing the postulation of potential outcomes and the related causal contrasts, and also the identification and estimation of these causal contrasts. And then the other pillar, the second pillar, is differential methodology based on ARIMA models that essentially involves predicting the outcome in the absence of intervention and contrasting it with the observed outcome. So this approach basically shares many features with causal impact by Brodersen, but it's based on ARIMA models, while causal impact is based on Bayesian structural time series models. So the way I see it is that it can be used as a frequentist alternative to causal impact, even because ARIMA models are very general, so they can be used to represent a wide class of processes from stock prices and even volatilities in some ways. And then they're also easy to implement because there are ARIMA routines already implemented in basically all statistical softwares. So let's shift to the first pillar, so the causal framework. Let me define with WIT the random variable describing the treatment assignment of unit I time t, where 1, as usual, denotes the active treatment and 0 denotes control. We will maintain the following assumptions. The single persistent intervention assumption, so every unit in our empirical application, we will be subject to a single persistent intervention, which is simultaneously applied on all units at time point s t star, such that all units are subject to control before t star, whereas after t star, they can either be always treated or always assigned to control. As a matter of fact, they will be treated. In particular, the observed series will be the treated series for every one of them, but we will see that in a while. I anticipate here that our empirical application will focus on a price policy applied by any silent supermarket chain. So at some point in time, denoted by this vertical line here, this supermarket chain decided to permanently reduce the price of selected store brand products. We focused on cookies in particular. So here you can see the price evolution, and that's the representation of our persistent intervention. At some point, they just reduced the price, and this price was maintained throughout the rest of the analysis period. The other important assumption that we will make is the temporal non-interference assumption, which is also known as temporal sutva. Essentially, this states that whether the other units are subject to the treatment or not, this doesn't impact the potential outcomes of unit I at time t. So these are only depend on the treatment path of that particular unit. Other two important assumptions are the following. So the covariance treatment independence assumption. So we included covariates in our model, as you will see in a couple of slides, to improve the prediction accuracy of the outcome, of the counterfactual outcome in the absence of intervention. But in order to do so, it's important that these covariates are not influenced by the treatment in the post-intervention period. And then the last assumption is this one, non-anticipating individualistic treatment assumption, stating that the probability of every unit of getting the treatment, it's individualistic, so it doesn't depend on whether the other units are assigned to treatment or not. And it's non-anticipating, so it just depends on past outcomes and past covariates. So all the assumptions are very important to define, estimate, and finally attribute the effect to the intervention. And also they allows us to use notation. Indeed, we can drop under assumption 1, we can drop the time subscript here. And under assumption 2, we can also drop the I subscript, because at the end we will do like a separate analysis on every product. So from now on, you will see that I will use this YTW, this simplified notation, to denote the potential outcome of a generic unit at a generic time in the post-intervention period. So under these assumptions, we can define the causal estimates of interest. In particular, we can start from the point causal effect, which is this tau t, and this is defined as a simple contrast between these two outcomes. So the outcome under treatment assignment W and the other potential outcome under the alternative treatment assignment W prime. This point causal effect is defined for every time point in the post-intervention period, so you can also sum them up to obtain the cumulative causal effect. And then by dividing this cumulative effect by the number of time points in the post-intervention period, you can get the temporal average causal effect. And in particular, this is the one we will focus on in our empirical application, and as we will see. So now let's switch to the second pillar, so the inferential methodology. As I told you before, this is based on ARIMA models. So here, I don't know if you can see the number, but this is equation 3. And essentially, this is an ARIMA model, PQ model. So these are Q, phi, P, L are Lag polynomials having roots outside the unit circle. And then, as usual, epsilon t is a white noise with mean 0 and some variance. The thing that is different from the usual ARIMA models is the last part, because there is this additional component tau t multiplied by an indicator function. And the indicator function is 1 if the unit is assigned to treatment and 0 otherwise. So that under this representation, tau t is the point causal effect at time t, as defined by the contrast of these two potential outcomes. So the outcome under treatment and the outcome under control. And another difference is that this ARIMA model is defined based on the potential outcome time series. So you can see the YTW here. So starting from this very easy representation, we can complicate things a little bit. So this is the most complex model that we can get. This is a seasonal ARIMA model. So there's the addition of the seasonal component here, and then there are the differencing operators if YCW is not stationary. And then also there's the addition of some covariates. But essentially, what I wanted to stress here is that even under this quite complex model specification, more complex model specification, tau c is still our causal effect, our point effect at time t. And after some manipulation, you can also rewrite equation 3 in this way. So based on ST, which is defined as a transformation of the outcome, where the transformation is the one needed to achieve stationarity. And then ST is also the transformation of Y minus, we subtracted some covariates as well, in a way such that ZT now includes only the stationary part of the model. And now we can denote with H0 the null hypothesis under which the intervention has no effect. So tau is 0, even not only in the pre-intervention period, but even in the post-intervention period. So that we can define the expectation of ST plus K conditionally on the past information set and under the null hypothesis. And we can denote that as hat S. This will be equal, since tau is 0, this will be equal to the expectation of ZT, the expectation of the stationary part of the model. And the important thing here to stress is that hat ST plus K is the closest approximation we can get to the counterfactual time series in the absence of the intervention, because this is the expected value of our potential outcome time series under the null hypothesis that the intervention has no effect. So every estimator will be based on this quantity here, as you can see from this slide. So for instance, the estimator of the point causal effect at time t star plus k, this tau hat, is basically the difference between the observed transformed time series minus the counterfactual series. So our approximation, our estimation of the counterfactual time series in the absence of the intervention. And then the other two estimators are defined as a function of tau hat. We can also show that under the model that we saw before, so under the model specification defined by equation 3 and under the null hypothesis that intervention has no effect, those estimators are normally distributed with mean 0 and variance is defined by these three equations, so that you can use the results of this theorem to perform inference on your estimated causal effects. And to sum up, so to estimate the effect of an intervention in a time series setting with using our approach, you need to follow these three steps. First, you need to estimate an ARIMA model, but just in the pre-intervention period. So to learn the dynamics of your dependent variable and the links with the covariates. And then based on this process, you can perform a prediction step to obtain an estimate of the counterfactual outcome in the post-intervention period. And finally, by comparing the observed time series with the corresponding forecasts, you can evaluate the resulting differences, which will be the estimated point causal effects. And finally, you can use the results highlighted by the previous theorem to perform inference, so to see if your, for instance, cumulative causal effect is significant or not. So I wanted to spend a few minutes on the comparison with the usual interventional analysis approach. Especially this approach here is a very simple approach that you can use in the econometrics literature under interventional analysis if you believe that your intervention has had a level shift effect on the outcome. Because here we are including a dummy variable dt, taking value 1 after the intervention and 0 before. And so that the beta 0, the estimated coefficient, gives you the size of the effect. And that's the level shift effect that you are assuming. However, what's the main difference between this approach and ours? Essentially, you have to be right about your assumption. So you have to be right about this level shift assumption. If you're not right, you can, of course, check the model adequacy by running some residuals analysis, for instance, and then you can, if you see that the model is not well suited to your data, you can change your initial assumption by including here pools dummy variable, for instance, or level or slope change. But essentially, this is a trial and error process, let's say, until you find a model that it's quite good for your data. Conversely, C-ARIMA doesn't assume any form, doesn't attribute any form to the effect. So we do not have to assume a level shift or a slope change. So everything can be estimated just in one step. And the second important difference is that even though you're right about this level shift, without a discussion of the fundamental assumptions underneath your model, you're not sure about this beta zero. So it can be an association, but you're not sure that this is a causal effect. This is an effect, but maybe it's not causal, it's just an association. So those are the two main differences between standard intervention analysis approach like this one or in our C-ARIMA model. We used C-ARIMA to estimate the effect of a real data application. We actually performed some simulations before, but because of time constraint, I cannot describe you the results of the simulations, but everything is in our paper that you can find on archive. So just a few minutes to describe this empirical application and the results. On October 4, 2018, the Florence branch of this supermarket chain store permanently lowered the price of several store brands, and we focused on the cookies category, where 11 store brands were subject to this permanent price reduction. And the interesting thing here is that for each of them, the supermarket chain identified some direct competitors that are basically identical to the store brands, but of course they sell under a different brand name. So they basically asked us to compute the effect that this price policy change had, both on the store brand and on the direct competitors. As you can see from this figure, they are really identical products. So we suspected that this price policy change applied on this first row of products here, the store brands, could actually have impacted in a negative way the sales of the competitor goods. So we considered every product to be treated under two different definitions of treatment, in a sense. Of course, for the store brands, the treatment was the permanent price discount. For the competitors, it was the relative price increase, because those two products are, if you consider, for instance, each pair of products, everyone is, they are identical, meaning that starting from this permanent price discount, competitors were immediately more expensive than the relative store brands. So they are indeed subject to an intervention. That's why we could assume absence of interference, because everyone is treated, even though under different treatment definitions. So we estimated independent models on every product. We included, as I said before, some covariates, in particular some of the week dummies and holiday dummies, and also the unit price, because you can't really model sales without including price. But price was the covariate receiving the intervention for the store brands. So we included the price that the store brands would have had in the absence of that intervention. So in particular, we have reason to believe that that price would be maintained at a constant level throughout all the analysis period. and this was based on the observation of the past price evolution. Yeah, so we have reason to believe that the price of the store brands would have evolved in that way. Very quickly, the application results. Those are the results for the store brand cookies, and we compared the two both approaches. So we computed our average temporal average effect and also the beta zero for REG-ARIMA at different time horizons, and we can see that it seems that this intervention had positive impacts on many of the considered store brands. Here there is also some residual diagnostics and the representation of the causal effect for a selected store brand. On the contrary, for competitor brand cookies, we do not find evidence of positive or negative effects. So basically, at the beginning, it was surprising because we were expecting a negative effect. But in the end, it can be that here there are some other factors driving consumer purchases, mainly subjective factors that we could not include in this analysis, like, for example, brand loyalty. So for some reason, even though there are store brand cookies that are less expensive, people wanted to buy, to still buy competitor brand cookies. So yes, in the end, we propose this novel approach to estimate the effect of interventions in time series setting. And we believe that this approach can successfully be used as the frequentist alternative to broader sense causal impact to estimate the effect both on a single time series and on multiple non-interfering series, providing also several improvements over the standard intervention analysis approach. We do acknowledge, however, that when used in our empirical context, this approach may suffer from some limitations, since we are not able to fully account for possible interactions beyond those stemming from price. So in a follow-up paper, we also considered a setting where we model each store competitor pair jointly. And this, we believe, that may partially overcome this limitation. Another thing that we can do is, if we are able to find a product category that did not receive at all the active treatment, it would be possible to employ a synthetic control approach, or maybe even better, synthetic difference in difference approach. This actually can be left as another follow-up for this analysis. So that's enough from my side. So thank you very much, and I'll leave you the stage for any questions.